Hey everyone, my name is Lottie DeWitt, and today's lecture is going to focus on the topic of integration. During this lecture, we will be going through an introduction to integrals, then look at definite integrals, including some properties of definite integrals, and also looking at the integral as an antiderivative. Then we'll move on to different integration techniques, including substitution, integration by parts, trigonometric integrals, and integration of rational fractions by using the technique of partial fractions. And finally, we'll look at improper integrals as well as multiple integrals. Our first topic is an introduction to integrals. So let's begin by looking at what integrals are. Integration is the reverse process of differentiation, which we will formalize later through the fundamental theorem of calculus. There are two types of integrals of a function f of x with respect to x. The first is definite integrals, which have integration boundaries denoted by a and b. This notation is understood as the integral from a to b of f of x dx and can be thought of as the area under a curve. The second is indefinite integrals, which do not have integration boundaries and correspond to the antiderivative of f of x. Note that a and b can be plus minus infinity, and there are ways to give a clear meaning to this. This is called an improper integral and will usually behave like a normal definite integral. In the following lecture, unless explicitly specified, we will assume that all functions are real functions of real variables. There are a few words of caution that one needs to consider. In this lecture, we will not go through proofs of existence, unity, or well-definedness. We will assume that all functions considered are well behaved. In particular, we will assume that all the functions inside the integration symbol can be integrated. However, please keep in mind that this is something you need to think about. For example, something like the integral of 1 over x dx from -1 to 1 is not well defined because 1 over x is not integrable between -1 and 1. Even though there are ways of making sense of this, we will not consider this type of case. Now that we understand what an integral is, we can look at definite integrals, including some properties of definite integrals, and also look at the integral as an antiderivative. In general, the definite integral of a function f of x between a and b can be thought of as a signed area under the curve of f of x between the points a and b. In the first case, the area is counted as positive, since the curve is always above the x-axis, while in the second case, the area below the x-axis is counted negatively. The original definition of the Riemann integral between a is equal to x naught and b is equal to xn is given by the limit of the Riemann sum. This is the sum of the areas of each of the triangles in the figure on the right. So the integral of f of x dx from a to b is equal to the limit as n goes to infinity of the sum from I equals 1 to n minus 1 of xi plus 1 minus xi times f of xi. This is rarely used in practice to calculate integrals analytically, but is the basis of numerical integration, which is not covered here but can be important. If f of xi is less than 0, then we can see that the corresponding rectangles will be negative. We can then look at the important properties of definite integrals. First is the concept of splitting the domain. If a is less than c, which is less than b, then we can split the integral into two sections over the domain, which is illustrated in the graph. The integral then becomes the sum of the two sections. So The integral of f of x dx from a to b is equal to the integral of f of x dx from a to c plus the integral of f of x dx from c to b. The second property is the concept of reversing the bounds of integration. This changes the direction in which you are integrating and causes an additional minus sign. So, the integral of f of x dx from b to a is equal to minus the integral of f of x dx from a to b. The third property is the concept of integration over a point, for example, a. This causes the integral to become 0. So the integral of f of x dx from a to a is equal to 0. The fourth concept, and one that is often used in mathematics, is the concept of linearity. If f of x and g of x can be integrated, and k is a constant, then the integral can be split up into its two parts. So the integral of f of x plus g of x dx from a to b is equal to the integral of f of x dx from a to b plus the integral of g of x dx from a to b. For k a constant, the constant can be taken out of the integral because it is unaffected by the integration process. So the integral of k times f of x dx from a to b is equal to k times the integral of f of x dx from a to b. Finally, we have the concept of order relationship. If f of x and g of x can be integrated and f of x is less than or equal to g of x for all x in the region from a to b, then the integral of f of x dx from a to b will be less than or equal to the integral of g of x dx from a to b. We should remember that the square bracket notation implies that the bounds themselves are included, where if you have curved brackets, then these imply that the bounds are not included. This leads us to the fundamental theorem of calculus, which, as the name suggests, is an important theorem to remember. The theorem states, let f of x be a continuous function on the region from a to b. For x in the region from a to b, let f of x equal the integral of f of x prime dx prime. Then f of x is differentiable on the region from a to b, and f prime of x equals f of x. So the integral of f of x dx equals f of b minus f of a. The first part of the theorem connects the notion of the integral to that of an antiderivative, while the second part tells us how to calculate these integrals. We should note that this implies that any antiderivative is defined up to a constant. Indeed, if f tilde of x equals f of x plus k, then we have f tilde prime of x equals f of x, and f tilde of b minus f tilde of a equals f of b minus f of a. This is what we meant earlier when we said that the antiderivative of f of x was given by f of x equals the integral of f of x dx. In physics and engineering, we often want to evaluate quantities of the form of the integral of f of x dx from a to b. When a closed form exists and can be found for the antiderivative of f of x, the definite integral becomes easy to calculate. We often use the notation f of x within square brackets from a to b to denote the integral of f of x dx from A to B. The fundamental theorem of calculus can be applied to this. First, we know that we can denote the integral of f of x dx from A to B equal to the notation using the square brackets. To this, we then apply the fundamental theorem of calculus to see that this equals f of b minus f of a. The hard part is to find the antiderivative f of x. We should be careful because it is not always possible to find a closed form for f of x, and sometimes finding the definite integral between specific bounds is easier. This table shows some basic antiderivatives that are quite common. The first is the function x to the n power. Its integral is x to the n plus 1 divided by n plus 1 plus the integration constant k. The second is the function 1 over x. Its integral becomes the natural log of x plus k. The third is e to the ax, where a is some constant. Its integral becomes 1 over a times e to the ax plus k. An example would be e to the 4x. Then the integration result would be 1 over 4 e to the 4x plus k, since a, the constant in this case, is simply 4. The fourth and fifth are the cosine of ax and the sine of ax. You can see that integration will turn a sine into a cosine and vice versa. But the transition from sine to cosine always comes with a negative sign. It should be noted that this is opposite to what happens when you differentiate, and the two shouldn't be confused. So the cosine of ax becomes 1 over a times the sine of ax plus k, and the sine of ax becomes minus 1 over a cosine of ak, or ax, plus k. One remark is that, more generally, if you know the derivative y equals f prime of x of any function f of x, then f of x equals the integral of y of x dx plus k. Let's then try an example to apply the concepts we've seen so far. We want to find the integral of the function f of x equals 2e to the negative x over 3 plus 1/2 cosine of pi x between 1 and 4. We start by writing the problem in the appropriate form for the integral we want to solve. So the integral of f of x dx from 1 to 4 is equal to the integral of 2e to the negative x over 3 plus 1/2 cosine of pi x dx between 1 and 4. We can then notice that there are two distinct terms, the 2e to the negative x over 3 and the 1/2 cosine of pi x. So we can use the property of linearity to break this integral into these two parts. It then becomes the integral of 2e to the negative x over 3 dx from 1 to 4 plus the integral of 1/2 cosine of pi x dx from 1 to 4. We can now see that both integrals have a constant inside them. The first has a factor of 2, and the second has a factor of 1/2. We know that we can apply the linearity property again to remove the constants from the integration. So it becomes 2 times the integral of e to the negative x over 3 dx from 1 to 4 plus 1/2 times the integral of the cosine of pi x dx from 1 to 4. Then we use the table of basic antiderivatives to apply the integration. The first integral has e to the negative x over 3. So looking at the table, we can see that here a is equal to negative 1/3. So the result is 1 over negative 1/3 e to the x, or e to the negative x over 3. The second integral has a cosine of pi x. And again, looking at the table, we can see that the a is pi, and so the result is 1 over pi sine of pi x. We didn't apply the boundary conditions from 1 to 4 yet, so we leave the results in the square bracket notation as a reminder that the bounds still need to be applied. We then apply the boundaries of integration, which results in negative 6 times e to the negative 4 over 3 minus e to the negative 1/3 plus 1/2 pi times the sine of 4 pi minus the sine of pi. And finally, we simplified to get the result, which is 6 times e to the negative 1/3 times 1 minus e to the negative 1 minus 1/2 pi. In the last line, we use the fact that the sine of pi is 1, and that the sine of 4 pi can be written as the sine of 0, which is 0. How many steps you take when solving an integral is up to you, but if you struggle with the practice, it's best to break it into parts and do each step at a time until it becomes more apparent to you. If we wanted to calculate the indefinite integral of the function f of x in the previous example, then we could have stopped at the fourth step and would not apply the boundary conditions. Instead, we would need to add the integration constant plus c to the end of the result. So the integral of f of x dx equals negative 6 e to the negative x over 3 plus 1/2 pi sine of pi x plus c. It is useful to consider the properties of the function. For example, the cosine of x is periodic with a period of 2 pi, and shifting the integration bounds can often prove useful. Often, these methods end up being limited, and we need to rely on specific integration techniques to help us. This leads us to the different integration techniques. In this section, we will go through substitution, integration by parts, trigonometric integrals, and the integration of rational fractions by using the technique of partial fractions. The simplest integration technique is integration by substitution. It relies on the connection between integration and differentiation, particularly the chain rule. We can see that d over dx of f of u of x equals d over du of f of u of x du of x over dx. And then this equals f prime of u of x times u prime of x, which finally equals f of u of x times u prime of x. The last line uses the fact that f prime of u equals f of u. Taking the antiderivative of this expression leads to f of u equals the integral of f of u of x times u prime of x dx. But by definition, we know that f of u equals the integral of f of u du. So we can see that the integral of f of u du equals the integral of f of u of x times u prime of x dx. This is a way of rewriting integrals that otherwise seem too complicated. It also applies to definite integrals, but extra care needs to be taken with the bounds. To use the method of integration by substitution, the steps are as follows. 1. Choose the appropriate u equals u of x such that f of u of x looks simple. This is where experience will go a long way, and the more problems you solve, the more intuitive it will become. 2. Calculate the actual substitution. We do this by calculating u prime of x to transform the dx into a du using dx equals du over u prime of x. For a definite integral, we also need to calculate u of a and u of b. 3. We substitute the terms appropriately. So we replace every occurrence of u of x by u. We replace dx by du over u prime of x. And for definite integrals, we adjust the boundaries of integration such that the integral from a to b becomes the integral from u of a to u of b. 4. This should make the integral possible to calculate explicitly. And 5. For an indefinite integral, don't forget to express f of u of x as a function of x and add the integration constant plus c. Let's look at an example of integration by substitution. Consider the function f of x equals the sine cubed of x cosine of x, and its antiderivative f of x equals the integral of the sine cubed of x cosine of x dx. We know how to integrate x cubed, and we know that the derivative of the sine of x equals cosine of x. So we can choose u of x equals the sine of x. We know that the derivative of u of x equals cosine of x. So we can write that dx equals du over the cosine of x. And so the cosine of x dx equals du. Knowing this, we can now proceed to solve the problem. First, we write down the antiderivative f of x equals the integral of the sine cubed of x cosine of x dx. We then modify this using our choice of u of x equals the sine of x and cosine of x dx equals du. So we can see that our integral becomes the integral of u of x cubed du. Using the table of basic antiderivatives, we can see that for a function x to the power n, the resulting integral is x to the n plus 1 over n plus 1 plus a constant. In our case, we can see that n is 3. So the result is 1 over 4 u of x to the fourth plus a constant. We then need to undo the substitution that we did earlier. This gives us the answer of sine to the fourth of x over 4 plus a constant. It's important to remember the constant in this example because we never specified the boundaries of integration. A second strategy for integration relies on the product rule of derivation. Here, uv all prime is equal to u prime v plus uv prime. Then, using the fundamental theorem of calculus, we can see that uv is equal to the integral of u prime of x times v of x dx plus the integral of u of x times v prime of x dx. If we can write the function we want to integrate as something in the form of u of x times v prime of x, we can expand it as the integral of u of x times v prime of x dx equals u of x times v of x minus the integral of u prime of x times v of x dx. This is called integration by parts, and its usefulness depends on how much easier it is to integrate u prime of x times v of x compared to u of x times v prime of x. Let's consider another example. Let's consider the integral from 0 to 1 of f of x dx is equal to the integral from 0 to 1 of xe to the x dx. As a product of two functions, it can be written as u of x times v prime of x. There are two choices here. The first is that we let u of x be x and v prime of x be e to the x. The second is that we let u of x be e to the x and v prime of x be x. Both choices are valid. We know the derivative and the antiderivative of e to the x and x, but only the first choice really helps us. Assuming this choice, we can then calculate u prime of x and v of x, where u prime of x equals 1 and v of x equals e to the x. We can then solve such that the integral from 0 to 1 of x e to the x dx is equal to x e to the x with bounds from 0 to 1 minus the integral from 0 to 1 of 1e to the x dx. We can see that then this becomes e minus e to the x with the boundary still from 0 to 1. And if we solve over the bounds, this gives us an answer of e minus 1, which equals 1. This example highlights the idea behind this integration strategy. But we have been lucky to end up with a simple choice for u prime of x times v of x equals e to the x, which we already had the tools we needed to integrate. In general, when dealing with the integral of u prime of x times v of x dx, multiple different cases can arise. The first is that we can be lucky and know how to integrate the integral of u prime of x times v of x dx directly. The second is that we might need to integrate u prime of x times v of x itself by parts, and sometimes even multiple times, and find a closed form for it. For example, you can try integrating f of x equals x cubed e to the x using this technique. Third, integrating u prime of x times v of x, sometimes by parts, yields an integral proportional to u of x times v prime of x. The terms can then be rearranged in order to give a solution. Fourth, if nothing else works, changing your choice of u of x and v of x might be necessary. For another example of integration by parts, let us try to find the antiderivative f of x equals e to the x cosine of x. Both e to the x and the cosine of x could play the role of u of x or v prime of x. but we will choose u of x equals the cosine of x and v prime of x equals e to the x. We can then note that u prime of x equals the negative sine of x, and u double prime of x equals the negative cosine of x, which equals negative u of x. So we start by writing out the problem we want to solve. So f of x equals the integral of the cosine of x times e to the x dx. We then rewrite this in the format of integration by parts. So f of x equals e to the x cosine of x minus the integral of the negative sine of x times e to the x dx. We can then see that we need to integrate by parts a second time. This means that f of x now equals e to the x cosine of x plus e to the x sine of x minus the integral of e to the x cosine of x dx. We can see that by doing this, we have recovered f of x. So f of x now equals e to the x times the cosine of x plus the sine of x minus f of x. Rearranging the terms to group the f of x terms on the left-hand side gives 2f of x equals e to the x times the cosine of x plus the sine of x. We can then divide by 2 to get back to only having f of x on the left-hand side. This results in f of x equals e to the x divided by 2 times the cosine of x plus the sine of x plus our integration constant c. In the last line, we added the integration constant plus c because we didn't have any boundaries of integration. And this is something that you have to remember. Integration by parts can be used to find the antiderivative of some functions for which we only know the derivative. If we let x prime be equal to 1, then we can always write that the integral of f of x dx is equal to the integral of 1 f of x dx. Rewriting this using integration by parts gives x times f of x minus the integral of x times f prime of x dx. If x times f prime of x can be integrated easily, then this gives us an expression for the integral of f of x dx. An example is the natural log of x. If we consider f of x equals the natural log of x, then f prime of x equals 1 over x. This means that the integral of the natural log of x dx equals x natural log of x minus the integral of x times 1 over x dx. We can see that simplifying gives that it's equal to x natural log of x minus the integral of 1 dx. Then the answer is that the x natural log of x minus x plus c, where c again is our integration constant because we don't have any boundaries of integration. Another example of integration by parts is the integral of the arc cosine of x. Using the substitution technique, the calculations are relatively direct. First, we use integration by parts so that the integral of the arc cosine of x dx is equal to x times the arc cosine of x minus the integral of x times the arc cosine prime of x dx. This then equals x arc cosine of x minus the integral of x times minus 1 over the square root of 1 minus x squared dx. We can then proceed to use substitution to solve the integral. So we let u of x equal 1 minus x squared and u prime of x equal negative 2x. So then dx equals negative du over 2x. We then put this substitution into the equation such that the integral of the arc cosine of x dx equals x times the arc cosine of x plus the integral of x over the square root of u times negative du over 2x. Simplifying this algebra leads to x arc cosine of x minus the integral of 1 over 2 square root u du. We can then write this as x arc cosine of x minus the integral of u to the negative 1/2 over 2 du. Solving the integral leads to x arc cosine of x minus a half times u of x to the half divided by a half. Simplifying algebraically, we see that the x arc cosine of x minus u to the x to the half power, which finally gives us the answer of x arc cosine of x minus the square root of 1 minus x squared plus the integration constant c. In the last example, we used the fact that the derivative of the arc cosine of x is negative 1 over the square root of 1 minus x squared. Using the properties of trigonometric functions and their derivatives is useful in combination with integration by substitution and parts. Here is a table of some useful derivatives. The function of the cosine of kx, where k here is always some constant, has the derivative negative k sine of kx. The function sine of kx has the derivative k cosine of kx. The function tangent of kx has the derivative k over the cosine squared of kx, which can be rewritten as k times 1 plus the tangent squared of kx. The function secant of kx has the derivative k sine of kx over the cosine squared of kx. The cosecant of x or of kx has negative k cosine of kx over the sine squared of kx. And finally, the cotangent of kx has the derivative negative k over sine squared of kx minus k times 1 plus the cotangent squared of kx. In addition to these derivatives, it is often useful to use trigonometric identities. One that we have hopefully all seen before is that the cosine squared of x plus the sine squared of x equals 1. We also have that the sine of some a plus or minus b equals the sine of a cosine of b plus or minus the cosine of A sine of B. The cosine of sum A plus or minus B equals the cosine of A cosine of B minus or plus the sine of A sine of B. And finally, the tangent of sum A plus or minus B is the tangent of A plus or minus the tangent of B divided by 1 minus or plus the tangent of A tangent of B. There are also the double angle formulas that use the fact that A is equal to B, and these have simpler forms that you might have seen before. The sine of 2A equals 2 times the sine of a cosine of A. The cosine of 2A equals the cosine squared of A minus the sine squared of A. The tangent of 2A equals 2 times the tangent of A divided by 1 minus the tangent squared of A. There are also equivalent expressions for the hyperbolic trigonometric functions, and those are things that you can look up if you need them. Equipped with this renewed knowledge of trigonometry, we can now apply it to the integration techniques we previously discussed. The steps are as before, except we are now looking for a substitution of the form x equals g of theta, where g is a trigonometric function. First, we choose an appropriate x equals g of theta. Second, we find g prime of theta such that you can write dx equals g prime of theta d theta. For a definite integral, you also need to calculate theta a equals g inverse of a and theta b equals g inverse of b. Third, we substitute the terms appropriately to find an expression which only has theta in it. We do this by first replacing every x by g of theta. Then we replace dx by g prime of theta d theta. And for a definite integral, we replace the boundary from a to b with theta a to theta b. Fourth, if this works out, then this should make the integral possible to calculate explicitly. And fifth, again, for an indefinite integral, we express it as a function of x, and we add the constant plus c. Let us consider an example. Consider the function f of x equals 1 over x squared plus 2 all to the 3 over 2 power. We want to calculate the integral of f of x dx from 0 to 1. We can notice that we have something like 1 plus x squared in the denominator, which means that we can try a tangent-based substitution. So, the integral 1 over x squared plus 2 all to the 3 over 2 power dx from 0 to 1 equals the integral of the square root of 2 over cosine squared theta, all divided by 2 tangent squared of theta plus 2 all to the 3 over 2 power d theta. We can then remove the constants from the inside of the integral to get the square root of 2 divided by 2 to the 3 over 2 power times the integral of 1 over cosine squared theta, all divided by 1 plus the tangent squared of theta, all to the 3 over 2 power d theta. Simplifying the constants leads to 1 over 4 times the integral of 1 over cosine squared theta, all divided by 1 plus the tangent squared of theta, all to the 3 over 2 power d theta. We can then simplify the stuff inside the integral, which leads to 1 over 4 times the integral of 1 over the cosine squared of theta, all to the 1/2 power d theta. And simplifying again, we see that we get 1 over 4 times the integral of the cosine of theta, d theta, from 0 to the arctangent of 1 over the square root of 2. Solving this integral gives 1 over 4 times the sine of theta from 0 to the arctangent of 1 over the square root of 2. And solving the boundaries of integration gives us the answer, which is sine times the arctangent of 1 over the square root of 2. Sometimes we encounter expressions that will look like ratios of two polynomials. One example is the integral of p of x over q of x dx, which, for example, equals the integral of 1 plus x squared divided by 5x squared plus 3x minus 2 dx. One trick is to use partial fraction decomposition, which means breaking down the function into a sum of simpler polynomial functions. If we can write the ratio as a sum of terms that look like a over bx plus c, or a over bx plus c to the power of n, we would be in an ideal position to integrate these, since from earlier techniques we know that the integral of a over bx plus c dx equals a over b times the natural log of bx plus c plus the integration constant k. And the integral of a over bx plus c to the power of n dx equals a times bx plus c to the power 1 minus n over b times 1 minus n plus the integration constant k. We won't be covering the technique of partial fraction decomposition during this lecture, but we will use the above as an example and go through that. For our example, let f of x equal 1 plus x squared divided by 5x squared plus 3x minus 2. First, we want to factor the denominator of 5x squared plus 3x minus 2. This can be done by finding the roots of the denominator. We can see that x equals -1 is a root, which means that q of x equals ax plus b times x plus 1. Filling out the information, we have 5x squared plus 3x minus 2 equals ax squared plus b plus a, all multiplied by x minus b. Then, equating the terms by power, we can see that a equals 5, b equals -2, and so q of x equals 5x minus 2 times x plus 1. The next step is to decompose f of x into a sum of fractions. Since p and q have the same degree, we should expect an extra polynomial term of degree 0, which is a constant. Thus, we are looking for an expression of the form f of x equals a over 5x plus or 5x minus 2 plus b over x plus 1 plus c. We then just need to find the coefficients a, b, and c. Starting from what we had on the previous slide, we want to find the coefficients a, b, and c. To do this, we start by cross-multiplying all the fractions to get them over the same denominator. This leads to a times 1 plus x plus b times 5x minus 2 plus c times 5x minus 2 times x plus 1 all over 5x minus 2 times x plus 1. We can then expand this such that we get ax plus a plus 5bx minus 2b plus 5cx squared plus 3cx minus 2c all over 5x minus 2 times x plus 1. We can then reorganize and factor out the x squared and x values, which gives us 5cx squared plus a plus 5b plus 3c all times x plus a minus 2b minus 2c all over 5x minus 2 x plus 1. We can then equate the terms by term, and we can see that 1 equals 5c, 1 equals a plus 5b plus 3c, and 1 equals a minus 2b minus 2c. We now need to solve this system of equations. We can see straight away that c is going to be equal to 1 over 5. Then we can use our linear algebra skills that we learned earlier to see that adding the second and third lines will give us 3b plus c is equal to 3b plus 1 over 5 equals 0. So b is equal to negative 1 over 15. And then the third line will tell us that a is equal to 1 plus 2b plus 2c equals 1 over 2 over 15 plus 2 over 5 is equal to 19 over 15. We will then move on to improper integrals. So far, all the definite integrals we have seen were bounded, meaning that we were integrating between two real numbers, and we assumed the function that we were integrating was continuous. This can be generalized to include functions with discontinuities and cases where one or both of the integration limits are plus or minus infinity. It becomes more challenging to prove formally that these integrals exist, which opens a whole new branch of mathematics, which is way beyond the scope of this lecture. Nevertheless, when the integral exists, it behaves as it should, except that instead of having the integral of f of x dx from a to b equals f of b minus f of a, we now need to consider the limit. So we have the integral of f of x dx from a to infinity equals the limit from b to positive infinity of f of b minus f of a. We can consider an example using the Lorentzian function. Consider the integral over the real line of the Lorentzian function, which is given by L of x equals 1 divided by 1 plus x minus x naught divided by gamma all squared. This is a function that appears frequently in physics and engineering, where x naught describes the position of the peak and gamma is a measure of the width. For the integration, we can use the method of substitution and let u equal x minus x naught over gamma. Note that the limit from x to plus minus infinity of u of x equals plus minus infinity. So then, the integral of L of x dx from minus infinity to infinity equals the integral of 1 over 1 plus u squared du from minus infinity to infinity. Looking at the table of derivatives of the inverse trigonometric functions, we can see that the value in the integral is an arctangent where k equals 1. We still need to apply the boundaries of integration, so we use the square bracket notation to denote the bounds from minus infinity to infinity. This equals the limit from u to positive infinity of the arctangent of u minus the limit from y to negative infinity of the arctangent of u. This gives us pi over 2 minus negative pi over 2. And so the answer is pi. The pink graph shows the version of the Lorentzian after the substitution, and we can see that it's now recentered and renormalized. We then move on to our final section on multiple integrals. We have stayed within the realm of relatively simple functions of one real variable, but we are often in need of integrating functions of multiple variables, such as the double integral of f of xy dx dy. This can appear, for example, when integrating a quantity that varies with position over a given area or volume, or a quantity varying spatially and with time. In general, when things are well defined, the way to calculate these functions is to separate the multiple integrals as nested integrals. So the double integral of f of xy dx dy can be written as the integral and then inside it the integral of f of xy dx and outside dy. And the order of the calculations, whether you do dx dy or dy dx, does not matter. In general, these multiple integrals can be interpreted as volume integrals, where we integrate over all possible positions of a point in a given volume. In this case, we call the volume element the term dx dy. Depending on the problem considered, it can be convenient to change the coordinate system. So, for example, from Cartesian coordinates x, y, z to spherical coordinates r, theta, phi. This corresponds to a substitution in the variables, and it is useful to know how to replace the volume element in 2 and 3 dimensions. First, we have 2D polar coordinates, which have rho and phi. In this case, dx dy is transformed into rho d rho d phi. Then we have 3D cylindrical coordinates, which use rho, phi, and z. And in this case, dx dy dz is transformed into rho d rho d phi dz. And we also have 3D spherical coordinates, which use r, theta, and phi. And in this case, dx, dy, dz is transformed into r squared sine of theta, dr, d theta, d phi. Let's consider an example looking at the volume of a sphere. To calculate the volume of a sphere of radius r, we can consider a function f of x, y, z such that f of x, y, z equals 1 if the point P equals x, y, z is inside the sphere S and 0 otherwise. It's easier to consider the problem in spherical coordinates, where small r equals the square root of x squared plus y squared plus z squared is less than or equal to r the radius. The volume of the sphere is then the triple integral over the point P in the sphere S over 1 dV. Rewriting this in terms of spherical coordinates leads to the triple integral of r squared sine of theta dr d theta d phi. We then need to add boundaries of integration such that we get the integral from phi equals 0 to phi equals 2 pi, the integral from theta equals 0 to theta equals pi, the integral from r equals 0 to r equals r of r squared sine of theta dr d theta d phi. We can then rearrange the terms to put the appropriate parts in the appropriate integrals, such that the integral from phi equals 0 to phi equals 2 pi d phi, the integral theta equals 0 to theta equals pi sine of theta d theta, and the integral from r equals 0 to r equals r of r squared dr. The resulting integrals give us 2 pi minus 0 times the negative cosine of pi plus the cosine of 0 times r cubed over 3 minus 0. And this equals 4 pi r cubed over 3. Next, let's consider the Gaussian integral. Consider the function f of x equals e to the negative x squared power. This is represented on the right. If we want to calculate its integral from negative infinity to infinity, even though it might not be obvious, none of the techniques that we have seen so far for integrating functions of one variable can actually help us to do this. However, there is a trick to performing this integral that relies on multiple integrals. The core idea is to consider a slightly different function of two variables. In this case, f of 2 xy is equal to e to the negative x squared plus y squared. And we're going to interpret xy as a point in a 2D plane. We will now find two ways to evaluate the double integral of f2 xy dx dy. First, we should note that f2 xy is equal to e to the negative x squared power times e to the negative y squared power. Therefore, the double integral of f2 of xy dx dy equals the double integral of e to the negative x squared e to the negative y squared dx dy. Again, we can rearrange the terms to put the appropriate parts in the appropriate integrals, such that the integral from negative infinity to infinity of e to the negative x squared dx times the integral from negative infinity to infinity of e to the negative y squared dy. We can then see that this is the same as the integral from negative infinity to infinity of e to the negative x squared dx all squared, which is just the integral from negative infinity to infinity of f of x dx all squared. Next, we can change coordinates and do the integration in polar coordinates. So, f2 of r phi equals e to the negative r squared power. We then perform the double integral again. The double integral of f2 of xy dx dy equals the double integral of e to the negative r squared r dr d phi. Again, we rearrange the terms to put the appropriate parts in the appropriate integrals. So the integral of e to the negative r squared r dr from 0 to infinity times the integral of d phi from 0 to 2 pi. The second part of the integral of d phi from 0 to 2 pi is just 2 pi. So we will put the pi out front and keep the 2 inside the integral for later. This gives us pi times the integral of e to the negative r squared 2r dr from 0 to infinity. Using substitution with u is equal to r squared and du is equal to 2r dr, we get pi times the integral of e to the negative u du from 0 to infinity. Solving the integral, we get pi times negative e to the negative u power from 0 to infinity, which gives us the answer, which is just pi. We now have two ways of expressing the same integral. Firstly, we have the double integral of f2 of xy dx dy is equal to the integral of f of x dx from negative infinity to infinity all squared. And secondly, the double integral of f2 of xy dx dy is equal to pi. This then allows us to solve the problem, such that the integral of f of x dx from negative infinity to infinity is equal to the square root of pi. This then concludes the lecture on integration. I just want to say that integration takes intuition, and that is something that comes with time and practice. One of the best things you can do is to find a good calculus book, which you probably already have from your previous classes, and go through and just do a lot of practice problems to help you develop those skills. I hope this lecture was helpful and gave you a refresher on the main tools of integration, which you'll continue using throughout your studies. Thank you.